Okay, let's get started here. So all of you should have your test number 1 back. Talk about that shortly. Just to give you an idea of where we're going in the semester here. Obviously, we're still in Chapter 3. Project number 3, I just posted it before class, so I will pass out a paper copy of it to you so that we can discuss it a little bit later. I anticipate that we'll be able to get through Chapter 4 and Chapter 5 before the next test, and that is tentatively scheduled for November 15th. Are there any questions before we start talking about the test? Okay. So the tests were relatively good in terms of if you look at the median there. I'd like to have more A's, but that's what we ended up having. So the median was 84%, which is pretty good. Actually a little bit higher than what I've had in the past. I don't really have too many comments about the exam itself, except for I wanted to discuss one part. It was problem number 2B. So in this particular problem, you had some simulated data, and you needed to find a studentized Bootstrap confidence interval for it. And where a number of students were having difficulty with was how to get V star. So how to get V star? And I asked you to use the non-parametric delta method. I had thought that by doing the non-parametric delta method in part 2A, I guess part II, that will lead you to figure out how you would actually then calculate V star. I'm not for sure why, but a number of you tried to actually derive what the actual V and then V star would be. And all you needed to do is exactly what you did in part 2. But now, instead of having a Y there, you have a Y star. Perhaps, in the, trying to hurry up and get done with the tests, you missed that, but in the end, it was a relatively simple aspect. Simple thing to do. Some of you also, I think, accidentally did 95% confidence intervals versus 90%. But that, I think lost maybe 1 point for that. Also, I guess I wanted to mention too, obviously be careful with the notation. If you have a star on something, that means a lot. It's a lot different than if you don't have a star on something. If you use a capital letter, that means a lot. It's a lot different than if you use a lowercase letter. Or, if you say, let's say TR star versus TR parentheses star, those mean different things. And a number of you lost some very simple points for those kinds of mistakes. And those mistakes are common. It's just you have to get used to the notation. Okay. So that's all I have specifically to say about the exam. If you have a question on why I took off a certain number of points on a particular problem in the exam, please come talk to me individually about it. If, however, though, you have a question about how to do a particular part of the test, please feel free to ask at this time. Are there any questions? Okay. So since we last had a regular class, too, we also have had project number 2 handed back, or returned to you, I should say. Are there by chance any questions on project number 2? Maybe all of you forgot about project number 2. Okay, we'll just move on. Any other questions before we get going on anything? So we are chapter 3. We were talking about some extensions of stuff that we were doing in chapter 2. Now extensions to the context of, let's say that you have more than one population that you're sampling from. And the way the sampling is done is that you get a sample from population 1 independently from population 2, independently from population 3, and so on. And so we looked specifically at one particular example that involved the difference of two means. So in this particular case, our statistical function looked like this. T of F1 and F2 is equal to U1 minus U2. And the corresponding plug-in estimate for the statistic of interest was y bar 1 minus y bar 2. We derived the non-parametric delta method estimate of the variance. We also talked about how the Jackknife could be used. We talked about how the regression method could be used. We talked about how Bootstrap could be used as well. And so the last time that we had a regular class, we had just left off talking about this two means example. And we're going to try to implement some of this stuff with respect to the difference of two means. So as we talked about last time, I'm going to have two different, going to sample two different populations. Sample size from population 1 is 20. Sample size from population 2 is 15. So these are not large samples. But we're still going to be interested in the difference of two means. And I purposely chose a skewed distribution, in this case an exponential, from which to take our samples from. And the reason being is because then you might be worried about, well, does the central limit theorem actually work out here? Since I have a small sample size. And so I put in Y1 my first sample, I put in Y2 my second sample from the two different populations. And then it's very important to understand the structure of the data. So I put into a data.frame the data in this structure. We'll use this structure a lot whenever we have stuff from more than one population. So from population 1, the data goes in first. Notice how I have a variable called Y. It has all my data in it. I have a variable called pop that corresponds to the population number. At the end of the data set, I have population number 2 data. So the first thing I need to do is write a calc.t function that's going to calculate y bar 1 minus y bar 2. But also I want to calculate 3 different measures of variance. Non-parametric delta method, Jackknife, and Bootstrap. For some reason I decided not to do the regression. Yeah. We'll just leave it at that. Okay. So this is my calc.t function. There's a lot of stuff to it. Put some of this stuff away. A lot of papers out. So this calc.t function, I'm going to pass in my data and my indices like usual. In order to do the bootstrap within this calc.t, I'm also going to pass in another argument called m to represent the number of resamples. So since my data is in a data frame, notice how I have to use, how I have to use I with that data argument. Notice I have an I comma there because I need to say which rows of my data frame to pull out for my resamples. Then, to find y bar 1 and y bar 2, I use a function called tapply. This is the first time that we've seen this function, but it's closely related to the apply function that we've seen before. What tapply allows you to do is, to some respect, like in this case, we think of like proc means with a by statement or even a class statement in SAS. Meaning that I'm going to apply the function mean to my data, specifically the y's, by population. So I have an x argument, an index argument for the by part, and then fun for function. I put into group.means, then these group means. The first element's going to be for population 1. The second element's going to be for population number 2. So I take the difference to get y bar 1 minus y bar 2. I'm working with the actual data. To do the bootstrap, just use the boot function like I normally do. Notice I have to write, of course, a new function to say, well, how to calculate my statistic of interest. So I have a calc.t2. We did this kind of stuff when we did the double bootstrap. So calc.t2, what I do, I get the corresponding resamples. I find the y bar 1 minus y bar 2 now in the context of these resamples, and then I return then the difference means. A key part here is this right here, strata equal pop, or $$pop. And we discussed this, I guess, a week ago Tuesday, and that is, since we are resampling here with respect to multiple populations, essentially what you have to do is a stratified sample. So I'm resampling within population 1, resampling within the population 2 original sample. You want to ask a question?
I do. Where does your calc.t, just regular calc.t, where's that function ending? Because I don't see a, oh, it's clear down there. Okay.
There's a lot.
Oh, right. Okay.
Sorry.
Okay.
Yeah, and just to make sure this is clear. So
Yeah,
what
yeah,
calc.t is going to do, once I actually implement it with the boot function, I'm going to calculate t star, vl star, vjack star, and vboot star.
So you're doing all.
Yeah, I'm doing all of
All right.
Okay, so don't forget the strata argument. You need the strata argument. Then I find N1 and N2, and also what would be equivalent to, let's say, S1 squared and S2 squared with the original data. So I use the t-apply function to get my sample size and also to do the sample variances. Now, where do I use these sample variances and these sample sizes? Well, to get VL, the non-parametric delta method, estimate of the variance. This, I'm not going to go over how this formula is derived because we've already done that last week. So it's just writing in the correct, writing the formula into the correct syntax. VBoot, just take the variance of the stuff that came from boot.res.m. And then I do the Jackknife. So L.Jack is the estimates of empirical influence values with respect to the Jackknife. So EMP, INF again. My data is in D. Notice my statistic, calc.t2, S type equal I, because I'm working with indices, type equal Jack. And again, notice you see the strata argument. You can't forget that, because you need to tell R that you're doing this Jackknife now with respect to you have multiple populations of your data. And then with my var.linear function, notice also I have to specify the strata argument. So I return difference in means, non-parametric delta method estimate of variance, Jackknife estimate, boot estimates. When I actually try it with my data itself, this is what I get. So here's y bar 1 minus y bar 2, VL, VJack, and then VBoot. I'm only using 100 resamples here, so I'm just testing it out. Now the whole purpose of writing this calc.t, to give you again, remind you the big picture here, is that what I like to do is actually calculate this stuff now for every single resample. So, because this is going to take a while, I'm just going to measure how long it takes using methods that we've done before. Then I used my boot function. Notice my statistic is now calc.t. I'm going to take 999 resamples. Strata equal set $1 pop. Again, I'm taking our stratified resample. And then how about at the second level resampling, I use 800. Then I print off the results.
Where does the set 1 come from?
Came from right up.
Oh, okay.
So this can take some time to run. My old computer took 12 minutes, and for some reason I haven't updated to my new computer. I did run it before the class, and it took 9 minutes on my new computer. It takes some time, because you got the Jackknife to worry about, and also the Bootstrap, obviously. Now, what could you do with this? Well, you could form a Z star and, do confidence intervals for the difference of two means. I didn't do that here because, I do it later, I should say. What I was really interested in here, and the reason why I used 3 different variances, is what I was interested in was seeing how do these variances agree? Are they similar or are they different? And if they're different, of course, then that might make you worried about, well, is one of them wrong? Or are they all wrong? So that's why I actually did 3 different ways to implement this with these variances. I should also mention here too before we go on. Notice the QQ plot here of the T stars. What do you think about normality? So, it's questionable, definitely. Remember the central limit theorem. Y bar 1 minus y bar 2 for large samples should have a normal distribution. But what we see here is evidence that that sample size is not large enough, and the Bootstrap is allowing you to see this. In fact, you will see this sometimes in papers that someone wants to, let's say, examine if their approximation is working for a particular data set by implementing the Bootstrap. If their, let's say, normal approximation is working for a particular data set by implementing the Bootstrap or doing something like this. And so what this shows you is that, again, that we have the skewed distribution. We have 2 exponentials, and sample size of 10 and 15 are not enough for the central limit theorem to kick in. Okay, now let's look at how these variances agree. What you'll notice is that, and maybe I should change this next time, is that VL and VJack are exactly the same. So V star L and V star Jack are exactly the same. It's similar to what we saw in Chapter 2 when we just had, let's say, Y bar and cipher. Okay? So, perhaps I'm going overboard by actually showing you that indeed this is exactly the same when you actually take the resamples, but that's what I did. But you can also compare this now to V star boot, and you can see that the histograms are similar. But let's even go further. I got this idea actually from a paper that I did a few years ago, where I had a number of different estimators. I wanted to see for every single simulated data set that I'm applying with these estimators, or applying these estimators to, I wanted to see, are the estimators similar? I would hope they would be, but I was curious if this is true or not. So I came up with this idea of how to compare. I don't know, maybe other people have come up with this idea too, but I haven't seen others do this. And so what I do on page 311 is use what's called a parallel coordinates plot. Does anyone know what a parallel coordinates? Has anyone not seen a parallel coordinates plot? Okay, so about half the class. See, now if I would have, again, asked the question, has anybody seen a parallel coordinates plot? No one would have raised their hand. So that's why I always got to remember, you have to ask those kinds of questions the right way. So half the class has seen a parallel coordinates plot. Could someone tell me what a parallel coordinates plot is? You just forgot to raise your hand. Anyway, I will explain it. This is something that you typically see in a multivariate data analysis course. I know whenever I teach Stat 873, I make sure to cover it, and we use it a lot. I don't think Ken Eskridge, though, does. When he teaches it, he's been teaching it lately. Let's say that you have 4 variables in a data set, and you want to examine, you want to get a graphical summary of them. Could you do a scatter plot? Kind of hard to do a 4D scatter plot. Now there's techniques. What are some techniques in a multivariate class that you would use to view this data graphically? Excuse me?
Similarity stuff.
I'm sorry, yeah. Let me back up. Let's say you wanted to graph this. I'm just using, forget about the similarity stuff. Okay, all I'm saying is, how would you view a 4-dimensional data set graphically?
3D with different levels of the fourth.
What happens if they're all continuous? You're screwed.
Today, yes.
Well, one thing I'm sure that those of you who have taken Ken Eskridge's class was you could do with principal components. And that will allow you to plot, let's say, maybe 2 principal components with 3-dimensional, or 3 principal components, do scatter plots of them, and that will allow you to look at it. Any other ideas? Well, there's a variety of ways to summarize multivariate data graphically. I urge you to take a look at my Chapter 3 notes for my Stat 873 course. Some way would be, another way would be to do a stars plot. Another way would be to do what's called Chernoff faces plot. My favorite, though, is a parallel coordinates plot. And here's how it works. Let's change colors here. So you have, let's say, 4 variables. And suppose that you have rescaled the actual data values for all 4 variables, independently of each other, rescale to be on a 0 to 1 scale. So that, for x1, for example, its smallest value will be right here, if I were to plot it. Its largest value will be right up here, if you were to plot it. So you got all this rescaled data. And let's say you look at your first observation, and perhaps your first observation, x1, had a very large value relative to all the other x1 values. Let's say that it had kind of a middle-of-the-road value for x2. Here's x3, and here's x4. And then what a parallel coordinates plot does then, it connects them. Now take observation number 2. Maybe it looks like this. Looks like that. Observation number 3. Very low x2 value. So you could do this for every single observation in your data set. And what this will allow you to do is look at trends across the x1, x2, x3, x4 values. So for example, let's say if this plot had, let's say, 100 observations, and most of them follow the same path as observation 1 and 2. Observation 1 and 2. Here's observation 3. Then you would think observation 3 is, for example, an outlier with respect to x2. But, you know, other things that allow you to see is, for example, maybe, you know, you might see certain trends, like let's say high X1 values correspond to middle of the road X2 values, and so on. So it allows you to see multivariate data. It's very commonly used in a multivariate data setting. Now, what I wanted to do with this kind of plot was to examine, instead of X1, X2, X3, X4, how about we put VL here, VL star, V Jack star, and V boot star. And I have 999 of them, and this will allow me then to view how well they agree. If they agree then in value, then that suggests that you know, these estimates of the variances are doing about the same thing. If they disagree, then it will get me worried about if maybe one of these ways to estimate a variance is incorrect, at least for the sample size. Now, in order to fully understand this agreement, I have to make one change to a parallel coordinates plot and how it's normally done. And that is, I'm not going to rescale the y-axis. I want to keep that scale to be exactly the same. Now, why do you think rescaling is done normally with multivariate data?
Just the variance.
Well, the key is that you don't know what units, let's say, X1's measured in, or X2's measured in, or X3's measured in. You know? And so if they're not measuring the same kind of units, or they will measure the same thing, then that's why they're rescaling. Anyway, so I'll let you look at my code on your own. What I had to do was I took the par-chord function that's in the mass package of R, and I modified it, so I call it par-chord2, so that the rescaling didn't occur. And this is what I got. So, no way. I guess I have it up in the title. This is for the first 99 of the 999 variances that I'm calculating, or resamples that I'm doing. So V3 corresponds to V boot star, V jack star, VL star. And so what we can see here with the Bootstrap in comparison to the other methods of calculating the variance is that, you know, it largely agree. You know, sometimes it's a little bit higher, and sometimes it's a little bit lower. But overall, it's quite similar. And so what this does, it again reassures me that, yeah, the Bootstrap is giving us very similar results to what VL star is giving. So I'm satisfied with it.
What is that dark? It's kind of bold-minded.
It's hard to see. This is the average.
Okay.
The average of the variances.
Okay.
So the bottom one's...
That's what I thought it might be, but
yeah, the bottom one's for the Bootstrap, the top one's for non-parametric.
I probably already talked about this, I just don't remember. What's the advantage of using the boot? Why would we want to do that?
You're not using it on linear approximation. Okay, so you know, a useful tool. In fact, just to show you indeed that this is useful, I will show you real quickly a paper that I have published that has a plot like that in it. Well, this was 2009. It was published in Journal of Statistical Computation Simulation. That's a second-tier journal for statistics. Indeed. Eventually, there we go. I had 4 different methods that I was using to estimate a regression model, a logistic regression model specifically. And I also included some box plots so you can see what the variation was. And these are estimates of beta 1. So think of the slope parameter. And you can see that with the different method, it had the most variability. What was interesting that we got from looking at this, this plot, what we got from looking at this plot was that we thought was quite interesting that this random method, notice the smallest beta hat 1 right here, corresponds to With the different method, this I think the third largest beta hat one. So that got us a little bit worried about, those two estimation methods. They don't agree when they're estimating stuff on exactly the same data set. Anyway. Okay, let's continue here. Let's do some confidence intervals then. The regular old confidence interval that you learned for mu1 minus mu2 is y bar 1 minus y bar 2 plus or minus the value of 1 minus alpha divided by t quantile from a t distribution with, let's say, nu degrees of freedom, where nu comes about through a Satterthwaite approximation. So I'm not going to assume equal variances. And then we multiply it by this, square root of s1 squared over n1. I'm sorry, s1 squared over n1, s2 squared over n2. Something that you learned about in like Set 218 class. If you want to know how to do it in R, use the t.test function to do it. Note that there's an argument called var.equal, and I put false, so I didn't want to make that assumption. And here is my interval, negative 2.8 to 9.4. And what is the true difference? Mu1 minus mu4 is actually 14 minus 10, or 4. So yay! Confidence interval captured the parameter. Let's look at how we can do this stuff then with the Bootstrap. Again, just boot.ci. There's nothing really extra different that you need to do here, because since you included the strata argument in boot itself, boot.ci sees that and how it's doing the calculation. And so I'm going to do the basic and the studentized. And just because I can do this, we do know what the unbiased estimate of the variance would be. So why don't we just include that, and I calculate that actually above in the program. Take a look at the details if you want. Then how's it actually then using, or how's it actually calculating, let's say, V star for the Z star calculations? Well, it's going to look at the second element of boot.res $t, which will give us V star alpha. Okay. Then I go through some other implementation. I put the results in save one. I also look at some other stuff. Suppose instead we use then the Jackknife estimate for V star. Of course, it's exactly the same. I'm not sure why I did that exactly. And what happens if we actually use then the Bootstrap estimate for V star as well? I put this all together into a nice little data frame for display purposes, and this is what we get. All the intervals contain 4. The basic Bootstrap intervals may be the closest to the regular old normal distribution interval. Notice that the studentized interval is wider than the other two. It's shifted a little bit too. That's how you do the calculation. Notice how these intervals are quite similar, despite using this VBoot itself. It has a little bit of a different variance. And I just go on to show you what happens if you were to use VL instead of the unbiased estimate in the T plus or minus the quantile from the Z star distribution times the square root of V. What happens if you just use VL and there's an unbiased? And you get something similar. Okay, so that concludes section 3.2. Any questions? Yeah, let's talk about the project. Oh. Wow, that was pretty good that you were able to get that before class. That posted less than 1 hour before class. I would give you extra credit, but I think other students would be upset, so I'm not going to. Sorry. Okay, so problem 1, you have enough background to do now. Problem 2 relies on stuff that we're going to do later in Chapter 3. So since you can do problem number 1 now, and since that is the biggest problem here, that's why I wanted to give you this project now versus to wait. And before class, when I was going over my lecture notes, I realized, well, I haven't put the project out there yet. I guess I've been too concerned about it. I'm actually writing project number 5 for you guys right now. And I've been too concerned about that and focusing on that I forgot that you don't have the paper copy of project, or you didn't have project number 3 out there yet. Anyway. Okay, look. Computer crashed before class, so I had to get my project back. Get that copy back again. Computer. Let's see. Sorry. Okay. So we've kind of had a theme this semester with these projects on working with variances. I thought, why not continue with this? But now, since we have 2 populations, we need to have 2 variances. And how do you usually compare 2 variances? You usually take the ratio. So why don't we do some stuff with the ratio of 2 variances? So let's let y1 be distributed f1, y2 be distributed f2, and we're interested in this as the statistical function. So T of f1, f2 is sigma 1 squared over sigma 2 squared. Of course, we can write this out as integral of y1 minus mu1. Mu1 is mean for population 1. df1, got square there. Integral of y2 minus mu2 squared df2. Okay. So with that as a setup, I want to do some stuff with the ratio of 2 variances. First of all, part A. What's the plug-in estimator? Called t-plug. That should be kind of easy based on what I just showed you there and based upon stuff that we've done in the past. I'm going to put the hat on top of the F. Go with it. Part B. Derive the non-parametric delta method estimate of variance for t-plug. So what this is doing is basically using stuff that's on page 3.1 and 3.2 of the notes. Derivation is going to be a little bit more difficult than what we did with mu1 minus mu2, but it uses the same basic concepts. Part C, let's get some data and do some calculations. So let's simulate some samples from F1 and F2. We're going to work with small sample sizes because I want to see what happens when you do have a small sample size. And we're simply going to work with 2 normal distributions. Notice SD1, I'm sorry, the standard deviation for one is 1, standard deviation for the other one is 2. So then sigma 2 over, oops, sorry, I want to make sure I get the order right. Excuse me. So sigma 1 squared divided by sigma 2 squared is what? 1/4. So we know what it is. So I simulate the data, and similar to what we did with that exponential example, I put my data into something called set 1, and this is what you get. Rerun my code, make sure you get exactly this. Once you get this, calculate the empirical influence values for the data using both your derivations from part B and the EMP-INF function. Note that I did not show you in class how to use that function with respect to the non-parametric delta method. It's a little tricky, but I want you to have the experience of figuring out how to use the EMP-INF function. Of course, you will need to use a calc.tw-like function that we've done in the past. You're going to also need to use a strata argument when you call this function. And the tricky part is to make sure that R is constructing its data correctly inside of calc.tw because, of course, you have stuff from two populations. That's the tricky part. You know, one thing that I did first was I worked with the y bar 1 minus y bar 2 example to make sure that I got the right answer. And then based upon what I had done from that, then I transferred it to this project, now for a little bit more complicated example. But remember, too, that as long as you did your derivation correctly in part B, you will know what the correct answer is for part C. So you know what you're shooting for. I think that's often very helpful when you're doing homework problems or projects and stuff. Okay, so that's part C. Part D, now let's estimate then these empirical influence values with the Jackknife and regression-based methods. So I showed you basically how to do the Jackknife earlier. And just to make sure that all of you get the same answer, I give you some number of resamples, and also I tell you to set a particular C. Part E. Let's change the statistic of interest, let's call it T, to basically S1 squared divided by S2 squared, so the unbiased estimates. And let's redo some of these calculations now using the Jackknife and the regression. This part E is motivated by, I think a number of you have been concerned that we've been using the bias estimate of the variance itself in Chapter 2. You've been concerned that, well, are we going to get good results? Are we going to get the right variances? And so I purposely put this problem in here to show you that, indeed, you're going to get just about the same results. Okay, so compare your estimates to those found in Part C and D. Provide specific reasons why differences or similarities occur. Being very specific. Part F. Now do the bootstrap. Okay? Again, remember you're going to need the strata arguments here. And part G. Part G is a very good problem. Often I get a question of, well, how do you know that your variance is correct? How do you know that you're estimating the variability correct? How do I know that the Jackknife's working? How do I know if non-parametric delta method is working? How do I know if the bootstrap's working? How do I know? And then this is a bigger research problem, or I should say, this is a bigger problem that not necessarily in our class, but outside of this class, when you're doing research. As many of you, what you're going to be doing if you're getting a PhD in statistics and you are going to then do the dissertation, you're going to have to derive a variance. How are you going to know that this variance that you derived is correct or not? There's a number of ways to figure this out. Here's one way using Kernel Simulation. And in fact, this is the exact same method that my PhD student, Bowen Zhang, is using for his dissertation. And Bowen is defending, if you are interested, if you want to see actual implementation of doing something like this. He is defending on October 22nd at 11 a.m. Way upstairs in room 901. So 11 a.m. is just the normal summer. Anyway, so what do we do to make sure that, or to verify that indeed our variance estimates are correct? What I've done here is I've kind of outlined an approach versus give it to you all at once. Plus this also helps me grade a little bit easier. So the first thing I want you to do is simulate 500 data sets using the exact same settings as given at the beginning of the problem. Don't use a for loop when you are actually simulating data. In other words, what you need to do, suppose you create an object called B, set it to 500. Put n1 times B here, put n2 times B there, and now you got your data. Now note, you do not necessarily want to create this set 1 right away. Okay? Display the first and the last data set simulated to make sure, and I'm going to use that then to grade that you did it correctly. Because I obviously have done it to myself and I know what they should be. Part 2. For each simulated data set, calculate the variance estimates for t using each of the 4 methods examined in this problem. So notice t here is being used. So I'm using s1 squared divided by s2 squared. I'm using the 2 unbiased estimates of the variance. So calculate the variance estimates for t. So we talked about Jackknife, we talked about the regression method, we talked about the Bootstrap method. But as you will see, even if you use the non-parametric delta method, which has a different version of t, you're going to see early in the project you're going to get about the same results. So I want you to use the non-parametric delta method estimate as well. As a way to verify for me, when I grade your project, verify that you did it correctly, display the first and the last variance calculated for each of the 4 methods. So you're going to have 500 variances for each of the 4 methods. Part 3, average the variance estimates for each method over the 500 simulated data sets. Okay, just find your averages. Now part 4. This is when we figure out, well, what is actually the variance? And we have 4 estimators of the variance. What is actually the variance? Estimate t for each of the 500 simulated data sets. Calculate the sample variance across these estimates of t. In other words, just a regular old sample variance that you would use for a sample size of 500. And notice what's in there, t. T sub b is the estimate of t for the b data set. T bar is then the average across all 500 data sets. The resulting sample variance is a Monte Carlo estimate of the actual variance of t. Since this has a large number of samples, of course, and we know that from the weak law of large numbers that this is going to get to about where you want it to be. That's why this is an estimate of the actual variance. It's going to be a very good estimate. So what you need to do then is what you got in part 3 from your estimators. Compare them to what the actual variance is. If what you get in 3 is about the same as in 4, great. Your estimators are working. If it's not, then you have to be worried about, well, are these estimators doing what they're supposed to do? Maybe my estimators are not correct. You will see some differences. So don't be alarmed necessarily if you don't get all of them, or maybe even any of them, to match. Now part 6. How about you repeat this process now for sample sizes of 100? Since they're larger sample sizes, you would think that if these estimators are correct, they're going to show themselves to be correct for these larger sample sizes. So try it out, see if it happens. You will get stuff to start working out. Maybe if it didn't work out here.
You go to what?
Sorry. You will get stuff to work out. In other words, you will start seeing the estimators to be close to the actual variance. So again, what this is going to, so it's a nice problem. I really like part G. It's just, it's often a little bit hard to explain because it's not, obviously it's not in the book. But this is how, in a research setting, you would verify that if you have derived a variance, you would be able to verify that, and indeed it's doing what it's supposed to be doing. So you can use this technique for papers, for example. Okay, so project number 3, we'll say a tentative due date is October 18th, so Thursday after fall break, 2 weeks from today. I want to be done with Chapter 3 before it's due. I anticipate we will finish Chapter 3 sometime next week. Okay. Are there any questions? And we'll talk about problem number 2 next week as well. Again, you are welcome to work in groups. I recommend it, but if you don't want to, I guess that's okay. Okay. So, now this takes us to section 3.3. Section 3.3 talks about semi-parametric models. So, semi-parametric means you're somewhere between non-parametric and parametric. So you make some assumptions, but not necessarily as many assumptions as you would with a full-blown parametric analysis. Here's an example of a model that would be used in a semi-parametric setting. Suppose that we have our indice I denotes population number, and indice J represents the observation number, or you might even say rep, replicates. So let's say y sub ij, meaning your response for population I, or I guess you can even say treatment I, and observation J, is set up to be as follows. Mu sub I, so let's say the mean for population I, plus sigma I, the standard deviation for population I, times a random error term. It's called epsilon sub ij, where we define epsilon sub ij as IID 0, 1, mean 0, variance 1. Notice I'm not saying a particular distribution, though. Thus, this is why this is semi-parametric. But this is a common setting that most of you should, or I should say, all of you should be used to seeing something like this. But typically, you say epsilons are normal. Okay? Here, I'm not saying that. And also, make sure you realize this too. Expected value of y sub ij is equal to what? Here. Mu sub I. The variance of y sub ij is equal to what? Sigma I squared. Okay. Now, one of the really nice aspects of a model like this, and you'll see this a lot in this semester, especially in Chapter 6, is that while the y's have, let's say, different distributions, the epsilons don't. They have exactly the same distribution, no matter what the population, let's say, number is. Exactly the same. And this then allows us to take advantage of that as aspect when one is taking resamples. So in the previous section, when we took resamples within a population. So if I have two populations, I'm going to take resamples from, let's say, population, or let's say sample number 1, and then I'm going to take resamples separately then for sample number 2. Here, in this particular case, since we have a common distribution that all of them share, we will see very shortly a way that we can take resamples for both populations from the same underlying distribution. Okay. How about we call this distribution for epsilon sub ij F0, for lack of a better designation. Then what we like to be able to do is estimate then the EDF, or come up with the EDF for the epsilons. Well, how do we estimate the epsilons to begin with? Well, you could simply rewrite your model so that you have epsilon ij here is equal to mu sub ij minus mu sub I over sigma I. course, we don't know what mu is. We don't know what sigma is. So how about we just put hats on top of them? And then instead of calling this epsilon, how about we call E instead, like we do normally? And those are my, let's say, you could say semi-studentized residuals. Well, why am I calling them semi-studentized? Well, that's a common term that I use, for example, when I teach Stat 870. The variance of y sub ij minus mu hat sub ij is not sigma hat squared I, because we have this extra estimator there. So that's why it's a semi, let's say, studentized. People might have other names for it. Just that's the name that I use. Semi-standardized. Instead, what one could do, a studentized quantity or standardized quantity, would be this. Let's call it E tilde, where I put this little adjustment here. All of you have heard of a hat matrix. All of you should be familiar with this idea of this adjustment. It comes from a hat matrix. Semi-studentized residual, E tilde, just has this little extra adjustment here. And where does that come from? Well, if I were to find the variance of y sub ij, I could have put a mu hat sub I here. I just put a y bar instead, because how would you estimate mu I anyway? Just the sample mean of the y's. So I put a y bar I there. And you probably have all went through this kind of derivation before. And you get sigma sub I squared. There's 1 minus 1 over n sub I. And fortunately, my i's for some reason are not coming out very well. I noticed before class that I forgot to put an I on the ends. So just make sure you put i's on the ends. So now, the mean of E tilde is 0, and the variance of E tilde is 1. Okay. Now these E tildes have a common distribution. If the sample sizes were different, notice that the E tildes would not, the E's themselves would not have a common distribution. So now that these E tildes have a common distribution, we're going to take advantage of that when we take our resamples. We are actually going to take resamples from these E tildes. We're not going to take resamples directly from the Y's. We're going to go to the E tildes because of this common distribution. Our book calls these resample values E star sub ij's. Now, they could have put a star on top of the E tildes. They just decided to call epsilon star sub ij. And so I'm just going to do the same thing. So what this means, and I'm going to just simply take resamples from from all the E tildes, without respect to, is this E tilde basically from population 1, or is it from population 2, population 3? I don't care. I'm going to just randomly resample these E tildes. So for example, and this can be as often confusing for students with respect to the notation. So let's say that I have, let's see, n1 is equal to 3, n2 is equal to 2. Okay, very small data. So that means I have an E tilde 1, 1, E tilde 1, 2, E tilde 1, 3, E tilde 2, 1, E tilde 2, 2. Right? Now I just want to resample from these 5 things like I would normally. So maybe the first one that I get is E tilde 1, 3 in my resample. Maybe the next one that I get is E tilde 2, 1. Maybe the next one I get is E tilde 1, 3 again, perhaps. And this is where the notation gets a little weird. since this E tilde 1, 3 was the very first thing that I resampled, in my notation, I'm going to denote it as this. Epsilon star 1, 1. So, if you think of all your epsilons that you have, the very first one that you would have would be for population 1, observation 1. So we call this E tilde 1, 1. The next one, E tilde 1, 2. And the next one, keep on calling it E tilde, I'm sorry. Epsilon star 1, 3. Now, notice here this subscript 2 on the second element of my resample. It's a 2, meaning it came from population 1. I'm sorry. Gosh. I'm making it even more confusing. The 2 there means it comes from population 2. But in terms of my resamples, I'm going to say that that's going to be designated as population 1. Is everyone clear on this so far? Any questions? It's more complicated than what it really is, but from past experience, students have had some problems with this. Okay, some notes. So we're still taking resamples from F hat, which is now just simply the EDF, the E tildes. That's it. And we call it what's, yeah. And one of the main points is that the E tildes are all identically distributed. Thus we have a larger set to resample from if instead we just resample from within population I. Think about, we've discussed the discreteness that can come into play when you're working with a non-parametric bootstrap. And if we were actually taking resamples within our original samples, within our original populations, when you have N2 equal to 2, think about how discrete things are going to be and how that might perhaps cause problems since it's so discrete. Here we have a larger set of things that we can do our resample from. Okay, so we have these epsilon stars. What do we do with them? Well, we use them to find our y stars. That's the whole purpose of doing what we're trying to do here. We want y stars. So we're going to set y star sub ij to be equal to the observed mean plus the observed standard deviation times epsilon star. So for example, y11 star is equal to mu hat 1 plus sigma hat, and then based upon my little example, E tilde 1, 3. Y12 star is going to be mu hat 1 plus sigma hat 1 times E tilde 2, 1. That's how I form my resamples, or the y stars, I should say. Now you can work with these y stars like you would know. That's it. Now, this idea of how to take the resamples, I think I briefly mentioned this. It's going to be very important when we start talking about regression analysis in chapters 6 and 7. Why do you think that this is going to be important in that setting? Think about what your y's would be in a regular old regression model. Are all your y's going to have exactly the same distribution? Let's think of a normal linear regression model. Do your y's have exactly the same distribution? Typically you assume constant variance, What about the mean? Will the means be all the same? No. Here's your regression model. This is what I'm doing in my Stat 870 class right now. Expected value of y sub I is equal to beta 0 plus beta 1 times xi. Now, obviously, they're not going to have the same distribution, unless all the x's were the same, but if all the x's were the same, why are you using regression analysis in the first place? Okay, so because of this then, in chapter 6 and 7 then, what we're going to do is the same idea that we're going to be working with some form of residuals, make some modifications to them so they have the same distribution approximately, and then take resamples from the residuals, and then use those to reform our y subs. Okay. Here's another way to think about what we're doing. In this little example where we had 5 observations, you could say that we have the following indice pairs. So, for example, this 1, 1 is representing population 1, observation 1. The 1, 2 is representing population 1, observation 2. All we're essentially doing is this. Our y stars are equal to mu hat plus sigma hat times an e tilde where I randomly select the indices from those 5. That's another way to think about what we're doing. Any questions about that? Okay.
So you won't necessarily get the same values of your y's back. Well, if you start, never mind.
Yeah, well, yeah, you won't. Okay. So that's one way to approach the problem in a semi-parametric manner. Now, another way to discuss things in terms of a semi-parametric manner is to make some kind of distribution assumption, but not a full one, but in a different way. And so this is in particular often done in hypothesis testing. Or let me restate this. Often we need to change the EDF. We're doing a non-parametric bootstrap. Often we need to change the EDF in a particular way from being just a regular old EDF to being something else that allows you to incorporate a particular assumption about F. I'm not saying necessarily normality. I'm just saying some kind of assumption. So for example, this is often going to happen in Chapter 4 when we do hypothesis testing. Now, when you do a regular old hypothesis test, you assume that your sample comes from a distribution under the null hypothesis. You assume the null hypothesis is true, and so you have, let's say, a null hypothesis distribution. Let's call it F sub H0. Then, using that, sampling distributions for your statistic of interest, such as T, are derived assuming that the null hypothesis distribution holds. So in a resampling setting, then, when we do bootstrap hypothesis testing, we can't just use F hat itself, meaning your observed EDF. We're going to have to change F hat so that the null hypothesis would be true. More on this in Chapter 4. The example that we're going to look at is actually example 3.4 in the book. And that says, what happens if you could assume that you have a symmetric distribution for your data, or that for a particular population? Now, I'm not talking about multiple populations anymore. Suppose you have one population, and you could assume that you have a symmetric distribution. you wouldn't want to then resample directly from f hat. You would want to resample from an f hat that reflects the symmetry. Well, how do you get a symmetric distribution if f hat is not actually symmetric to begin with? Well, here's how. Well, let me, excuse me. Here's how. Change your EDF to consist of, like usual, y1 through yn, but also to have n more observations represented in it. These observations are 2 times mu hat minus y1, where mu hat is the estimated median, through 2 times mu hat minus yn. Why would you want to do that? Without looking, hopefully you didn't look at my comment about why. It basically gives you kind of the other side of things, you could say. I know at least when I first read this example, when I was taking this corresponding course, it wasn't obvious to me why it was, and I had to have my professor explain it to me. But this, which, by the way, who was my professor? Tom Logan? The one that I did the book review with? Anyway, hopefully you saw that in the extra credit. So mu hat's the median. So now, what if you had a purely symmetric distribution, then you would expect this to happen. Mu hat plus the deviation of y from mu hat. That to occur with the same probability as this, mu hat plus mu hat minus y minus mu hat. So notice what I'm doing here. I'm basically looking at my data, first of all, from a point of view, what's the deviation from the middle? Y minus mu hat. And if I had a symmetric distribution, I would equally observe stuff above mu hat as I would below mu hat. Look what happens then if I actually do a little algebra. Mu hat, the mu hat disappears, you just get y, right? So your mu hat plus y minus mu hat. Down here, I would have 2 mu hat minus y. And so that's why then we need to construct an EDF in this manner. Unfortunately, now that takes us to a point where we are out of time. So we will talk about the actual numerical implementation of this example, how to actually do it in R next time. Are there any questions? Okay, that's it for today.